Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering the Module 6 Inquiry Question 3 of the HSC Physics syllabus. This is the 2019 HSC Physics paper Question 24, and it's all about transformers. We have a step-up transformer constructed using a solid iron core, as you can see here. The cores are made using copper wires of different thickness as shown. You can see different thicknesses here. The table shows electrical data for this transformer. We have the voltage of the secondary coil, the current of the secondary coil, and we have the total power of the first primary coil. Let's go to the first part of the question. The question says, explain. So I'm going to circle that. How the operation of this transformer, so we want to look at the operation of the transformer, remains consistent with the law of conservation of energy. Okay, we want to do that. And we want to include a relevant calculation. So what we want to show firstly is if it is following the law of conservation of energy, that means the power going into the system and the power going out of the system should be equal. Okay, power is given as voltage times current, so we can write it out like so. I know that the power going in is 500 joules per second, and I can work out that the power coming out is 450 joules per second. So if I look at that, the values don't seem to match up. Okay, so how can I demonstrate why it's still consistent with the law of conservation of energy? And we can start by the first point. Okay, so the law of conservation of energy has two parts. Energy can be transformed, or energy can be transferred. Now clearly in this case, energy hasn't been transferred from our primary to secondary coil. Most likely it's been transformed into some type of other energy. In this case, from electrical energy into heat energy. Okay, so firstly what you can say is the operation is still consistent with the law of conservation of energy. So operation is consistent with the law of conservation of energy. The reason being is there is an energy transformation. Okay, so energy transformation Okay, so we're saying that energy is being transformed from electrical into heat energy, which means the missing 50 joules per second most likely was converted into heat, or potentially a bit of light as well, if there was so much heating that light was produced. Okay, so there's that. Okay, so that's where the missing 50 joules per second most likely have been. If we account for that missing heat energy as well, then we should be able to find it's still consistent with the law of conservation of energy. Okay, so there's that. Okay, so that's that. Question B, it says, explain two modifications to this transformer that would improve its efficiency. So what we mean by efficiency, we're talking about ensuring that the power transfer from here, or this way around, sorry, because that's the primary, from here to here is as close in terms of the values as each other. Okay, So if we have a look here, we can see there is a thickness of wire. So having thicker wires will ensure that the resistance is lower. So thickness will, or higher thickness will reduce resistance. Lower thickness will increase resistance. So what we can do is potentially increase the thickness of our wires on our primary coil. That will reduce the overall resistance of the electricity being transferred through the coil here. That's the first thing. What we can also do is, if you recall, on the iron core itself, as we're causing a change in flux, so we're going to induce EMF onto this iron core. According to Lenz's law, this EMF is going to try and oppose the change in flux that's causing it. So it's going to be an EMF that opposing the change of flux here. So that reduces our overall efficiency. So what we can do to decrease these eddy currents forming is by creating sort of laminations. Obviously it's not quite like that. So if we look at it from the side, we try and break it down into sort of cut thin slices. So you got lamination, you've got changing the thickness of the wire. Another way you can do it is by changing the iron core, so using ferrites, which are really good magnetizing material, but really poor conductors of electricity. So there's like 3 different ways you can go about it. I'll try and write all 3, but the question only requires 2. It's just good so that you remember the 3 types of suggestions. Okay, so let's go into our first modification. We'll say this one is to change the thickness of the primary wires. Okay, so increase thickness. Call it the primary coil. Okay, so of course this isn't explained, so what is the benefit of doing this? So the effect is to increase the thickness, or the cause is to increase the thickness, but what's the effect of doing that? And so by increasing thickness, we decrease resistance as the particles can't collide as readily with the wires, and that will reduce the overall resistance of the initial electricity transfer. Okay, so we have a lower probability of collision with the metal lattice. So that decreases potential energy loss. And hence that improves the overall efficiency of the electricity being transferred into our iron core. Okay, so that's our first modification. The second modification we're going to go with is laminating the iron core. We'll do that in another color. Modification 2. The lamination of the iron core. So why do we want to do this? This is going to reduce the size of the eddy currents. So eddy currents will still form, but it will reduce the overall size, and so we get a less opposing force countering the net change in flux we're experiencing. Okay, so by reducing the size of the eddy currents opposing us, we will also improve the efficiency in which the overall change in flux is, or the overall induced EMF is transferred into our secondary coil. So I just added an extra bit. By reducing the size of the air currents, we reduce the opposition it has to the EMF transfer we're trying to include here. So those are two reasons. I'll include just one more. Like I said, the question doesn't need three, but just one more so you know what the third potential modification can be. So modification 3 is to use ferrites or iron oxides. Okay, now the purpose of the iron oxide is we'll still get the formation of eddy currents, but because they're really poor electrical conductors, the eddy currents won't be able to revolve around the actual core to oppose the changing in flux that we are seeing here. So a good magnetic material, that means eddy there will still be a change in flux. So change in flux still occurs. So it still allows for the production of EMF in the secondary coil because it's a good magnetic material. So they're still changing in flux. But because it's a really poor electrical conductor, the eddy currents cannot transfer around the core to oppose the changing fluxes between the two coils, okay? So because of that, it won't oppose the changing in flux we're causing in our transformers. And so all these methods, all these modifications, all these will improve the efficiency of transferring energy. Okay, so hopefully that gives you a better detail of how law of conservation of energy works with transformers, and also how the efficiency of transformers can change depending on the types of modifications used for it. If you found this video useful in explaining and breaking down the exam question, please give it a like to support other videos to come out, and thank you for watching.